classical computer, it will not take the values in between zeros and 1. It may take either 0 or it may take 1. So in the few mathematicians are identified a fuzziness. They imported the fuzziness into the classical physical system, and then they arrived the values in between zeros and 1. But in the qubit is nothing but this is also a quantum physical system, but it yields one of two states when is measured. So either 0 and more than 0, or when 1 and less than 1. So it is getting two states simultaneously. Either it is a 0 and more than 0, less than 1, or 1 and less than 1, more than 0. So this is the concept of superposition principle. So the quantum mechanical regime that the objects do not manifest only a single state. So it is going to be assume all possible state. That's why it is called superposition principle, superposition state. Coming to the entanglement. Superposition principle and entanglement are the fundamental concepts of quantum mechanics or quantum computing. So here entanglement is nothing but, so here we are two or more quantum systems share one quantum state. We have only one quantum state. That one quantum state is shared by two and above, two or more quantum systems. So this kind of concept is called as entanglement in quantum computing. So here two or more systems shares a single quantum statements, two or more systems combined and holding a single quantum state. So here two or more systems can perform multiple calculations simultaneously, whereas classical computers, that is normal bits, cannot do this. So the speciality of this is simultaneously we can perform more calculations, multiple calculations. So this is called quantum parallelism. But in the classical computers, this is not possible. But in a recent days, scientists are trying to identify the teleportation with the help of quantum, and once the error is very minimum, then this is a qubit level, then obviously teleportation will be possible. So according to Google, according to IBM, according to Azure, Microsoft, it is possible, teleportation is possible when the error correction are very less. So once we identify the error, then we need to reduce the error. Once we started to reduce the error, then teleportation are possible. Okay. In the normal classical bits are use NOT gate. So when it is 0 and then the output of the input is 0 and then the output is 1, and when the input is 1 and the output is 0 for the NOT gate. But in the entanglement, it uses controlled NOT gate. So what does controlled NOT gate means? So it's a 2 qubit gates. These 2 qubit gates combinedly processed, and then the output is named as controlled NOT gate. So we can call it as C NOT gate. So superposition principle and entanglement are key fundamental concepts of quantum computing. And then how to explore this quantum computing, exploration of quantum computing. So here we are going to identify the difference between the classical computer and the quantum computer, bit and quantum bit, qubit, bits and qubits, regular computing techniques and quantum computing techniques. So we need to classify or emphasize or identify the difference between these two. So in classical bits may use discrete value as well as continuous value, but in the quantum computing may use continuous values alone. Like that, we need to identify the difference analytically, numerically. So these kinds of solutions, that is analytical solutions and numerical solutions, may help us to identify some kind of possible output in various complex field. So that initially Grovers and Char identify some kind of algorithm to overcome some complicated problem and to improve some complicated data processing capabilities. So initially Grover did use some kind of searching techniques. So searching techniques means it is not a properly sorted database. In that improper or unsorted database, Grover identified to retrieve the data with some kind of keywords. So that kind of algorithm is called as Grover's algorithm. If it is a sorted data, then we can retrieve the data, but it is an unsorted data. So in that unsorted data, he used some kind of searching techniques, and then he retrieved that data. But the speciality is this algorithm, Grover's algorithm, quadratically speed up the search methodology. That is double the speed up process, and then we will get the output when 50% of the time only this qubits quantum computers are used, whereas classical computers utilized 100% of time. But this, according to the Grover's algorithm, this Grover's algorithm quadratically speed up the process and get the output. We get the data set for the unsorted databases also. Coming to the Shah's algorithm primarily focus on integer factorization. This integer factorization yields the exponential decay. So coming to the integer factorization is nothing but, suppose I'm going to a number, we can consider 60 means I'm going to write 60 as 3. So here I have to check prime numbers. So obviously 3 is a prime number. So I cannot do anything with the prime number. So I'm going to keep 3 as it is. Then I need to make, this is non-prime number. I need to make this as a prime number. So how can I make this as a prime number? 5 is my prime number. Then 5 into 4, I can write 5 into 4. But again, this is my prime number. This is my prime number. 4 is not a prime number. So again, I have to make it this as a prime number. So 3 into 5 into 2 into 2. So these are all the integer factorization. So in this way, we need to do the calculations. So short division. Shaw did these kind of calculation with the help of integer factorization. This yields an exponential decay. Actually, we have two types of this quantum computing deal with complex problems. Complex problem means we are including the imaginary identity named as I, and then Euler's identify the imaginary identity with the help of exponential, that is e power I theta. E power I theta is nothing but cos theta plus I sin theta, and e power minus I theta is nothing but cos theta and minus I theta. That E stands for the exponential. Here, for example, as I told you, 60 can be classified into 3 into 20. 3 is a prime number, 20 is a non-prime number. We have to make it 20 as a prime number. So 3 into 5 into 4. Again, 3 is a prime number, 5 is a prime number. Again, we have to make it the non-prime number as a prime number. 4 is a non-prime number, make it 2 into 2. So 60 can be written like 2 into 2 into 3 into 5. So 60 is a big number while comparing to 2, while comparing to 3, while comparing to 5. So in this case, we are going to decay the numbers with the help of integer factorization. Shaw did this kind of concept for the decay the values. So once I know how to decay the values, means the same kind of techniques can be applied to after identify the errors. We can apply the same techniques, because once after identify the errors, if my error is a 7, then I need to reduce the errors, like it should be at least a 6 point or 5 point or 4 point. So for that, I need some kind of decaying techniques. So Shaw identified exponential decay by applying some kind of integer factorization concept. And then the application of this integer factorization concept and exponential decay involved by Shaw is very much useful in the drug discovery. So we can give the personalized medicine to the patient. For example, if someone is in high fever, then the doctor may suggest him to take Dolofor 650. If someone are in a somewhat less fever, then 500 mg, the Dolofor 500 mg he may suggest. But nowadays, once this integer factorization algorithm techniques were implemented, and then based on the exponential decay, if one patient, based on his temperature, we can personalize his medicine, like we can give us as a 280 mg, develop 280 mg or 250 mg or 350 mg or 400 mg. So for drug discovery, this concept will be very much helpful. So if we want to write a coding related to this, means you should be very much for very much uh, knowledge in integer factorization and exponential decay. So many decay concepts are there. So you sure identify the exponential decay and integer factorization problem. So you can write a code in any software languages, but the base and fundamental concept behind this is integer factorization. Based on the integer factorization, we can apply the exponential decay. The two, when we go for the exponential decay, Euler and complex, these things are work under complex scenario only. So obviously you should use e power, either e power I theta or e power minus I theta. According to the domain, you have to choose the exponential concept. And then the next one is scalability. So then, as I said, in quantum computing, we are focusing scalability and error correction. These two concepts are very important in quantum computing. So coming to scalability, of course, it's a physical qubits. Then this physical qubits used to high level physical qubits used to lower the error. This is called scalability concepts. Scalability concepts are nothing but we have to use high level qubits to lower the error. So if you are focusing on physical logical qubit, then you have to use high level physical logical qubit to lower the error on physical logical qubit. Again, as I said, if we done it in a proper manner, we can reduce the noise. If we did it in an improper manner, the noise level, that is the error level, will increase like anything. In that case, we may lose some data, and then in that case, we can lose some data, and then data retrieval is somewhat difficult once we did not follow the scalability. And then in the scalability, once we identify this, once we started to use the scalability in a proper manner, we can avoid major issues related to the particular problems. So once the scalability and redundancy also, once we started to use the scalability, then we can avoid more major issues. And then it is a continuous process. So as I said, it is not a discrete process, it is a continuous process. So the difference between a discrete process and the continuous processes, so we can use the summation for the discrete process, and we can use the integration for the continuous process. So whenever we have a single value as a output, then we can use it we can bringing those problems into the discrete values. So when we have the solutions, that is either it is a numerical solutions or it may be an analytical solutions, and the analytical solutions later converted into the numerical solutions. So those numerical solutions are not in a crisp manner, that is, then we should go for the continuous series. So continuous series means we should have we have to integrate the lower limit and upper limit. Then we will get then it is comes under the continuous process. We never face any kind of discontinuity under the process. That's why we are bound with continuous process. So we should not go for the discrete process. When we go for the discrete process, we will end up with some single value as the output. So we can use some kind of techniques like induction techniques and so on. But in the continuous process, if discontinuity occurs, then it will obviously automatically quit. So, so you cannot get the proper output. The program will quit in the intermediate level itself. So that's why it is working in the continuous process. So so this continuous process may leads to so many quantum circuits, and then all these quantum circuits involves qubits only, not the ordinary bit, the way where the classical computers use. Then some challenges in the quantum computing and its development. Of course, from 2016 on, from 1985, from the 1985 onwards, the quantum computing is slowly started, and nowadays Azure Quantum, Microsoft, IBM, Google are processing this. But here some challenges we are facing. So what kind of challenges, what kind of technological hurdles we are facing here means obviously scalability and reliability. How long the qubits will exist, there is a question mark. And then scalability. So as I said, the scalability is if more physical qubits are used per logical qubits, the lower the error of the logical qubit. If you use more qubits, then lower the errors. So we have to get the more qubits. So that how can we get the more qubits means again we need to go for the NISQ, that is noisy intermediate scalable quantum computers. So those computers only will give higher qubits to us. With that higher qubits, we need to lower the rate. So we have scalability, and then it should be exist. It should be reliable. Our higher qubits should be reliable for some period of time. So for that consistent period of time, this should be reliable. So that we have to wait, and then we have to periodically observe the pattern of our higher qubits. Then how much it has oscillates. So when observing the pattern only, we can identify the qubits level. After that only we can either go, if it is oscillate more means we need to go for the control theory, then we need to control the qubits according to that. So scalability and reliability is a challenging one. And then the another challenges is fragility and external noise decoherence. Fragility in the sense the quantum state of qubits is very fragile, and that is some kind of perturbations, that is slight vibration or change, any concepts vibration or change, for example based on the temperature, some kind of changes are there means it will affect the entire system uncontrollably. We cannot do anything. So we may lose some kind of information also due to this fragility. That is fragility in the sense some some perturbation or some kind of slight variation or some kind of a change, any changes, that is a delta value. If you project delta value here, delta means it is a difference operator, it is a small quantity. So when you identify a small quantity, that makes a huge sense. So that may last some kind of data. So fragility we need to focus when we process the data, when we write the code, we need to focus the fragility also. And then interconnection between two qubits. And coming to decoherence, in quantum coherence, it is a process that occurs when a quantum system interacts with its own environment. Whenever it it is working in its own environment, sometime it may lose some kind of its quantum related property. Sometimes its behavior may be unchanged behavior may be changed like classical computers behavior. So though it is qubit, sometimes it may qubit in the sense greater than 0 and less than 1 value simultaneously it may hold. But when the system is reached the decoherent statements, even it is in the qubit state, but the qubit property may last. So qubit property may last means again it will act like a classical computer. That is, it is, even though it is a qubit, it will act like a bit. So it may lose its own quantum property. So that we have to focus decoherent state also. So these are all the challenging one when we go for the development or computational development of the quantum computing. Okay. Mm. I actually quantum computing, what kind of algorithm I need to focus with? This algorithm is very good or that algorithm is very good. Of course, I speed up the process, and then what kind of realistic assumptions I need to go, what kind of process I need to follow, what kind of computing architecture I need to follow means the answer is it's very crucial to identify one particular algorithm or one particular architecture or one particular process. It depends upon the situation. It depends upon the gate which you follow. So X gate, XOR gate, C NOT gate, NOT gate, AND gate, OR gate, something like that. And then once the bit can be converted into the qubit, then your gate also will change. So once your gate also will change, the speed of the particular gate will change automatically. So once it is changed, the connectivity process also will change. So so many factors are there, so we cannot identify this algorithm is best for computing architecture or focusing the real life or real world problems. So and then this algorithm will speed up the process. So still the world is not yet revealing this kind of algorithm to us, even though IBM is doing some kind of research work, and Google, Azure, Microsoft are doing some kind of research, but they are not revealed these algorithms or these computing architecture to the world till now. So it depends upon the situation, it depends upon the assumption we have, it depends upon the coordinates we have, we can choose our own algorithm. So many algorithms are there, so we'll see the algorithms one by one later. So it depends upon the algorithms. You can use 9 bits or 7 bits or 5 bits or few bits, 4 bits, and so on. We can use any bits. And then what kind of architecture support I can get to reduce my error correction? So here, long range interactions between two physical qubits should plays a vital role here. Long range interconnection between physical qubits. At least we need, this is basic and this is fundamental. If you have a long range interaction between physical qubits, surely you will get some kind of feasible solution. But if you have a strong fidelity and strong rate of long range interactions between physical qubits, then you can overcome the error. So here fidelity means fidelity is also a quantum state measures, and then but this is like a two, it closer to two quantum states. Two quantum states are closer to each other. So here these two quantum states are closer to each other, means this will help us to arrive there or access the accuracy state. And then, or if I want to transfer some data, and then the data sender and receiver date can be identified in a proper manner. So that I need to use some kind of threshold value, some kind of logic gate value, some kind of fault tolerant technique we have to follow here. So once we have a long range interactions between some kind of physical qubits, then I can identify some and reduce some kind of errors. And then if it is comes under the fidelity in the sense two or more qubits are closer to each other, and then this may leads to some kind of accuracy state, then it will be very useful and easy to reduce some error in as I told, in the recent year Google arrived from 3.1 to 2.9. So of course 0.2 is the difference, but anyhow this leads to the higher changes. Then the another portion is, as I said, fidelity is nothing but two quantum states coming closer to each other. This may lead to some kind of accuracy. So in the complex situation, in the complexity, so we can focus this as nearest neighbor interactions. So it is scientifically speaking nearest neighbor interactions. So this code which we have to focus should rely on nearest neighbor interactions. So this nearest neighbor interaction leads to limited connectivity only. So this limited connectivity focus the superconducting devices again. So these are all not possible under the classical or normal bits. So these are all the minimum level of error correction techniques we need to support. And then the next one is low density parity check, quantum low density parity check codes. Then this codes play a vital role nowadays. So here the error rates, whatever the error rates may be, so and in nowadays 0.1 level of error rate reduction in quantum means that is a great achievement. Suppose if I have a huge error rate like 20, 30, my expected output is 80, and then if I got a 50 means my error rate is 30. So in that case, it of course it's a numerical value, so you can have it on any percentage or percentage. So in that case, we have to make it as one. You have to reduce at least 1%, means you have to follow the low density parity check, quantum low density parity check codes. So this code will focus in this code simultaneously focus the threshold value and then logical gate value and then fault tolerance technique also. And then here we need some kind of hardware long range connectivity also. So when we go for the threshold level and then reduction of higher level of reduction of error rates, if our errors are more, then the best way to get for the coding is quantum low density parity check code. So with that code, at least we can reduce the error at 1% itself. 1% level, we can reduce the error. So that we have so many operators. What kind of operators means some operator and poly operators are there. Mathematically speaking, and that the poly operators, mathematically speaking, the poly operators should have a complex matrices, and then this is traceless and involutory property, unitary property, it may satisfy. But coming here, as I told, scaling redundancy plays a vital role in error identification, error correction. So wherever we have, once we did it in an improper way, the value may be rise. If you use it in a proper way, obviously we can reduce the noise. So we have to focus the scaling attributes. We should focus the scaling attributes. This attributes also in the distributed level, not in the centralized level, because we are in continuous system. So once you go for the discrete systems, then you can choose the a centralized system. But here we are in the continuous case. So in that continuous case, so once you go over the continuous case, it's better to do the distributed quantum systems. So wherever you have quantum systems, so you are going to process the qubit to identify to get the solution of some kind of problem. So you have to get a computational solution for some kind of problem in the distributed manner, not in the centralized manner. So that we have to use unitary operations. So what is a unitary operations means? We need to go with, for example, suppose it is a matrix. So in unitary operations are nothing but let us assume is my universal set. Then unitary operation means, and then like I'm going to consider u star and u equal to I. So what is I is nothing but identity operator. U star is nothing but adjoint of the matrix U. So this is called unitary operator. So U star into U is equal to I, or U star equal to I. U star equal to I. So this is called unitary operator. So I is nothing but identity operator. U star is the adjoint of U. So this is called unitary operator. So the system should follow the unitary operator. It has to be follow the distributed systems, not in the centralized system. So once you follow the unitary operator, that is comes under the matrix, and then you have to, once it is a matrix means you have to check for the some basic properties of matrices. It is a traced matrix or traceless matrix, involutory is there and unitary is there. You need to check all those things, and then some kind of gate values also we have to check simultaneously. So if it is a qubit means, obviously we have to check C NOT gate, controllable NOT gate value we need to check. Again, here we have to focus distributed system only, not with the centralized system. And then the third assumption for scalable distributed computer quantum system is nothing but we have to identify the objective function, and then that objective function should maximize the value. So what is our objective function? Objective function is nothing but ultimately we have to use the scalable in a proper manner. That is scalable in a scalability should be properly distributed in the qubits. So that is our primary goals. So in that, once you did it in a proper way, so obviously you will reach your objective. So what is our objective? Reduces the noise. So reduction of noise is nothing but the maximize the solution. So you can use the objective function. Once the objective functions entered, once the objective function entered means you have to find out the optimality of your objective function also. These are all the inbuilt or hidden value, hidden things we need to do. So objective function is derived or identified or determined. Then you have to, obviously you should maximize the objective functions, that is obvious. And then in that case, in addition to that, we have to check the optimality. So if you define the objective function, then the feasible solution will not reach the good solution. So you have to get the optimal solution. If it is not an objective function, it is a normal function, then you may get the feasible solution also. There itself you can stop the process also. But if you define the function as an objective function, then you should get the optimum solution. And then the next one is decoherence. You have to focus the decoherence. So decoherence, again, decoherence is also comes under the distributed system only. So, and decoherence in the sense, as I told, it is a quantum system. It interacts with its own environment, but when it interacts with its own environment, we may lose some kind of quantum behavior and quantum properties. So once it loses its quantum properties, that is qubit means, obviously it comes under the normal bits. So quantum computing we are not allow the quantum qubits to become a normal classical bits. So we have to focus that too. So the major drawback is we have to focus the scaling attributes properly. So when we go for the coding, when you started to write the code, you should focus the scalable attributes, scaling attributes. All the values, all the process should be distributed manner only, a distributed architecture only. It is not related to the centralized thing. And then follow the unitary operations. So when we do go for the calculations, we are in need of some kind of calculations, so go for the unitary calculations. And then define the objective function. Why we need to define the objective function means, obviously once you define the objective functions, obviously you will get the optimum solution. So that purpose you define the objective functions. Then decoherence. So as decoherence is nothing but sometimes when we go do all these process, we may lose qubits and then we may get bits. So to avoid this, we have to focus the situation and scenario, and then these are all the major problem we may come across when we go for the coding or when we go for the real-time implementation. As I said, once we go for the objective function means, our solution should be the optimum solution, that is optimization. So optimization, if it is a real function, or if our problem or our case studies are in a real situation, then we don't have any problem. If our problems are in the complex domain, so most of the quantum computing problems are in the complex domain only. So if our problems are in the complex domain, then our computers should perform faster than the classical computing. So we should get an optimum output, and then as well as we have to do some kind of interpretation and then get the optimum output, and then the two in the complex values, and then the solution should be faster than the classical computers. Few companies arrived in the logistics and manufacturing techniques, so they arrived at the optimum optimization also. So we'll see later on about this optimization on the logistics as well as manufacturing. So the Latin American group startup company called Quantum South arrived at the optimization. So not only that Quantum South, so in a similar way, Cambridge Quantum Computing, now it is merged with Honeywell Quantum Solutions. These two combinedly release QNLP, that is Quantum Natural Language Processing. So the quantum natural language processing, usually nowadays we know that how the classical computers do the natural language processing, but in the here the Honeywell Quantum Solutions and Cambridge Quantum Computing combinedly releases the QNLP, that is Quantum Natural Language Processing. So this is the ability to convert sentence statement into the quantum circuits, whereas the classical computing ability to convert one language of sentence into another language sentence. So you can use some kind of automata theory, and then with that automata theory you can convert the sentences into one form to another form of sentences. So with the help of classical computing, we can determine the automata concept, and then with that automata concept and CDNF, and then density function, we can use it, and then we can get the sentences in one form into then another form. But when we go for the quantum natural language processing, we can convert the sentence into the quantum circuits. With the help of Oxford based quantum computing research team, Cambridge Quantum Computing and Honeywell Quantum Solutions are converted the sentences into the quantum circuits. So these techniques, like a Cambridge quantum computing and Honeywell quantum solutions, their concepts are in their website. We can decode it, then we can do something with the help of Cambridge quantum computing as well as Honeywell quantum solutions. Once we at the end of my session, I will decode one research paper in quantum techniques based on mathematically. I will decode it. So once we know how to decode it, means either we can go with mathematically stronger, or we can go with the coding. We can either you can go with the product based, or you can go with some kind of code based. So or else data analytics also possible here. And then not only that, Honeywell and Cambridge, some other company like Thomas Ahmed from Max IT Healthcare, he also, along with his team, along with this group, invented some results, some quick results related to natural language processing. They are also our circuit level concept. Sentence, they converted the sentences into circuit, but in the early stage. Whereas in the classical method, when we go for more iteration, like 400 after 400 after 400 or after 500 iterations only, we can get the result. But when used for the qubit, that is quantum computing, a very early stage itself, you can get the result where we get the result from the classical computer. So and then with the help of this, we can give the personalized medication to the particular patient also. So they are identify, their team identify with the help of NLP, explainable AI, they identify the accountability in the field of medical field also. And then optimization techniques. So here, based on the optimization techniques, one cargo company arrived with the optimized, they are going to transport the goods from one place to another place in the aircraft. So in the passenger deck, they utilized the cargo things, and then they identify the better output. So one cargo company achieved this. So the cargo company is International Airlines Groups, IAG, achieved this. So and then they optimize the entire cargo carrier network like this. So they optimize the process only. Actually, in the classical computing, all the, you have to focus a set only. So the inputs are in the form of set only, but in the qubits, you have to exponentially decay the set. So once you decaying the set, you can subdivide the sets into so many subsets, and then you can exponentially decay the sets. So once you decayed the sets, so it is nothing but a subset. So once you got the subsets, then you can optimize the entire network, that is entire cargo carrier network. Again, that International Airlines Group people, researchers shared that they wanted to excited with further identification or further efficiency process. So innovative solution, they are looking for in more innovative solutions to improve the efficiency and improve the process. So they achieved their efficiency, they improved their efficiency, they improved their process with the help of some kind of findings. Though those findings improved their entire cargo carrier network. So these are all possible when they use quantum computing. So they told that their group, that is International Airlines Group, said that in that International Airlines Group, researcher named as Angel Capesa told that, so they identified the excited findings, and then efficient findings, improved findings, innovative solutions are possible when they apply the quantum computing only. So quantum computing only optimized this. So how the quantum computing optimized this? You need to identify the objective function. So the objective function itself, maximize or minimize function only needed to get this objective function. So there itself they identify. These are all the some hidden process of this. So how they achieve this means, so integrate the operational data into the algorithms. So they integrated some kind of optimization, integrated some kind of operational data into the algorithms. So for example, some kind of integrated operational data into the algorithm means, for example, we should have some kind of global schema, then heterogeneous source of schema, then mapping between these global schema and heterogeneous source schema. So if you integrated these data, then you can improve the performance of your operational data. So the integrated operational data is nothing but you should use some kind of schemas. So it should be a triplet. So it should be a triplet means first one is a global schema, and then the second one is heterogeneous schema, and then the third one is mapping between this global schema and the heterogeneous schema. So when you integrate these data in a perfect manner, that is, again you need to import the scalability, you need to import the integrity, and then redundancy also. So when you do it in a proper way, proper operations, like either you will go with the unitary operation or poly operations, then you will get the proper solutions. So when you go for the coding, so when we go for the codings, these are all the hidden techniques we should follow. And then, so what are the issues we have to we will get when we go for the data integration? So in data integration means schema, as I said, global schema, heterogeneous source of schema, then mapping between the global schema and the heterogeneous schema. So here schema integration means, again we have to follow the triplet. The first, in the triplet, let us assume G for global schema, and H for heterogeneous schema, and GHM means global schema, heterogeneous source, and then mapping between global and heterogeneous. So these are all the data we have. So you need to integrate these data. And then coming to redundancy. So coming to the redundancy, redundancy deduction. So redundancy is nothing but a mathematical operation, and it's suppose, let us assume we have some kind of equations, and then with that equation we cannot add anything or remove anything or modify anything, and it doesn't contribute anything related to the solution. Means we can remove that element, or we remove that coordinate, or whatever it may be, whatever you called it as. So that is called a redundancy detection. So suppose if you have an equation or inequality, whatever it may be, that doesn't add any new information or doesn't contribute to the solution of the problem, that is called a redundancy. Mathematically speaking, that is called a redundancy. So in that case, you can remove that particular part from your equation. So because that particular part only, your error rate becomes high. So you have to deduce this. That's why we have to focus on redundancy. And then a resolution of data value conflicts. So here the data value conflicts means discrepancies. If you have any discrepancies between the data in a single source, if you derived some data, in either it is a multiple source or in a single source. Multiple source means no problem. If it is a single source means, if any discrepancies between the data from the single source or single entity, then that is called a resolution of data value conflict. If it is comes under multiple source means no problem. If it is comes under the single source, then a single source and then discrepancy between the data from the single source means that is called conflict. So when we go for the in data integration, we need to focus the schema, redundancy, resolution of data conflicts. So these are all the things that we need to focus. So schema integration means, as I told you, we have to focus the global schema. So global schema means, obviously our data should be the metadata. Our data should be the metadata, and then these data should rely on some kind of a real world entity. We retrieved those data from the real world entities only. So after that, we need to segregate the data like heterogeneous data and non-heterogeneous data. Like that, we need to segregate the data. After segregation only, we will go with the mapping between the global schema and then heterogeneous source, or mapping between global schema and non-heterogeneous source. So these are all the. Hello, sir.
சொல்லுமா.
Yes, sir.
நார்மலா வேர்ல டைப் பண்ணுங்க. வாட்ஸ்அப் டைப் பண்ணுங்க.
Nothing, ma'am. You go ahead, ma'am.
Okay, sir.
Date of
So
birth,
these are
experience.
all called schema integration. So global schema, heterogeneous source, and then non-heterogeneous source, mapping between global schema and heterogeneous, and mapping between global and non-heterogeneous. So these are all the things we need to focus on for schema integration. And coming to the redundancy detection, as I said, redundancy in the sense, as I said, mathematically speaking, redundancy is nothing but any equation or any inequality that doesn't add or allow any new information or doesn't contribute anything to the solution. Doesn't contribute anything to the solution means we have to focus that kind of attributes, or we have to focus that kind of set. Whether your input is in the form of set, you have to focus that set. If your input is in the form of matrices, you have to focus that kind of matrices. So that is called redundancy. So once you identify those things, you can avoid the inconsistencies. So you may get the consistent solution. Once you identify the redundant concept, then your inconsistencies will move automatically. Your data set will remove the inconsistencies. Then obviously you will get a consistent solution, because we are in the continuous solution. In the continuous process, consistency should play a vital role. If you are in a discrete, then you don't bother about the consistency. But if you are in the continuous case, you should focus the consistency also. Inconsistency may increase your error. So how can you identify how can you remove the inconsistency means, just to do some kind of correlation analysis, Pearson coefficient of correlation, or you can go with any kind of rank correlation analysis. So you can identify the correlation. So correlation in the sense, the difference between two neighboring objects. If it is a complex numbers, the difference between two neighboring objects. Or else if it is a qubits, then decoherence concept. You have to focus the decoherence concept. So decoherence is nothing but two objects will come close together. In that time, you may lose the qubit concept. So once you lose the qubit, then you will become it will become a normal bit. So normal bit means quantum computing will become a normal computing. So you have to focus all those things. So once you process, then you have to parallelly check all those process. Once you already checked all those processes, surely we will get a proper code. And then data conflict. So data conflict, as I said, if it is in the single source, so same source, single source, you can derive the data from the single source, then there is no conflict between the single source of data. If it is a multiple source, then you may have some kind of complexity. But in a single source, you should not have any kind of conflicts. So that you have to check the abstraction also. So abstraction in the sense, it's a relevant task. So if any discrepancies occur, then what kind of deviation the data between have. So the discrepancy is nothing but what, some kind of conflict, some kind of deviation from the values. So what kind of deviation? So if it is converge, even though it is deviation, all the values are converging towards a particular value, then no problem. Suppose if any bits are started to diverge, then we have to give importance to this conflicts. So if it is, even though some conflicts are there from the single source of data, all those conflicts are travel towards a particular values, that is converge, then we don't bother. So we can carry forward those into the real world entity. If not, then we need to focus of that particular attribute. So that abstraction should be there. So here we can use some kind of some code. Then nowadays IBM is leading, and then again they introduce one chip, and then in that chip IBM give a IBM give a proper updation of modular quantum computing, and then they introduced one chip, and then that chip is called as Heron, and then that chip improves error correction, and then combating decoherence phenomena in the quantum system. So, and again, as I said, again we need to focus the error correction and then decoherence. So nowadays IBM did it. So now coming to the coding techniques. As I said, so many coding techniques are there in the real world phenomena. The first we'll see Peter Shaw's. He used a 9-qubit code. So actually 9-qubit code is a huge code. So we have to reduce the 9-qubit code as 8 or 7 or like that. So he introduced 9-qubit code, and then based on the 9-qubit code, he reduces the arbitrary errors in a single qubit. And then Andrew Stein, he found his code is called as Stein code. The latter it is called as a CSS code also. So, and then he modified or updated, or he again versioned it as 7-qubit code he used instead of 9-qubit. And then he also identified the arbitrary, he also reduces the arbitrary error. And then Raymond Laflamme, he again he decoded into 7 as 5, and then he also achieved, but he focused the fault tolerance. Andrew Stein and Shaw's focused error reduction techniques, and Raymond Laflamme focus on fault tolerant techniques. So initially it was a 9-qubit code, then it was a 7, and then it was 5. So when it comes under the 5, so again it is again everything is all the errors in a single qubit. So there in Andrew Stein also comes under the single qubit only. Why we can go with the single qubit means here once you go for the single qubit means you can have a resolution of data conflict. The resolution of data conflict will be very less when you go for the single qubit. When you go for the multiple qubit, surely data conflict will be there. To overcome this, they used single qubit. But even in the fault tolerance also they used single qubit. So against the error also, again Raymond Laflamme, he did not focus on errors. Initially he focused on fault tolerance, then he focused on qubit errors. All these codings are available in the internet, so we can get the sample coding also. But when we have a sample coding, so we should give the important to all the values like a scalability, we have to give an important, fault tolerant, we need to give an important, and then quantum decoherence, fidelity, operators, what kind of operators we have to follow, and then data integrity, and then optimization is there or not, and then schema integration, abstraction, data redundancy, resolution of data conflicts. These are all the things we need to focus, whatever your algorithm may be, whatever your bit level may be. Again, they combined classical computing and a Hamming code. They combined this, and then they also identified some kind of error reduction. So it is a classical code only, but they clubbed with the Hamming code and then trying to get a output like quantum computing. But they took 7-qubit code and 4-qubit from 4-bit, 7-qubit and 4-bit, 7-qubit and 4 classical bit, and then they try to reduce the error. And then this coding is called as CSS codes. CSS codes is nothing but the inverters, 3 inverters: Robert Calderbank, and then Peter Shaw, and then Andrew Stein. So based on their names, the inventor's name, we called it as CSS code. So they tried this in embedding coding also. So here quantum Hamming code, quantum classical Hamming code. So here quantum is 7 qubit and 4 classical bits. So they combined this, and then finally they called it as quantum Hamming bound. Again they tried into the single qubit, and then but here they try to reduce the Hamming code and increase the qubit, or decrease the qubit and increase the classical bits. But they identified that minimum they need 5 physical qubits needed to entered into the single qubit requirement. So this is some kind of combination of classical bit as well as qubit. And coming to the general cases, and additive code in the sense, when you go for the operators, you have to clarify your operators are based on additive or multiplicative operators. So for additive operators alone, and then a few codes are created by again Robert Calderbank, Eric Rains, and Peter Shaw. They identified a code. That code is called as additive code. And then these codes are also available in the website. So they arranged their codes into the square lattice format. And then the next important one is topological quantum code. So the topological quantum code is very much useful for error correcting code. When you focus error correcting alone, it's better to go with the topological quantum codes. So topological quantum codes plays a vital role in two-dimensional spin lattice error correcting code. So your dimension is two-dimensional, and you have a input is in the form of a spin lattice. It is in the form of lattice or spin lattice. Then if you want to go for the coding means, it's better to go with topological quantum codes, but it gives error identification, error reduction techniques only. So and then Toadburn and Steam constructed a entanglement techniques. So with that entanglement techniques, they identify a best stability formation between the sender and receiver. So and then authenticated and stability formalism between the sender and receiver was achieved by Toadburn and his team. And then again css code is nothing but uh, these three persons, Robert Calderbank, Peter Shaw, and Andrew Steen. So they wrote the code, css code, and then this code is running in 2D planar surface, two-dimensional planar surface. So once you want to go in the two-dimensional and then two-dimensional, either it is a spinned or unspinned, it's better to go with the topological quantum codes. So in the 2000 in this June 2024, they released 2D planar surface code with the help of topological quantum code. Previously no one identified this. And once they identified topological quantum code, we identified a quantum threshold theorem based on the topology only. So topology uses a CSS codes. So they also identify the threshold theorem. So the threshold theorem focuses on arbitrary length. So when you go for the computation, in the input, the arbitrary length of the input elements or arbitrary length of the content, then we can concatenate the quantum codes, CSS codes. Initially you have to decay the codes, then you have to pair the code, like a parity check. Okay, pair the code, and then that is concatenate the code. Then this leads to the quantum gates, and then we identify the numerical value below the threshold values. So this is also the optimum solution. So once you go for the quantum threshold theorem, you will get the optimum output. That is, you will get a value below the threshold value. So once the value is fixed means below the threshold value means, so error is somewhat reduced. So go with the threshold theorem. And then, so as I said, the growth of 2021, experimentally we realized the universe, the people from this world realized in the year 2021, entangling gate between two logical qubits are encoded. So once encoded, then topological quantum codes are generated. And then error correction codes are realized, and then yeah, the errors are reduced. Simultaneously, fault tolerance gene code also identified, and then fault tolerance code is nothing but what, even though fault is there, output will be there, but even though fault is there, but that output will be acceptable value. So that is called fault tolerance techniques, which was created by Steen code. So this result was proven in the year 2021. And then in the year 2022, some researchers from the University of Innsbruck, they didn't focus on error correction. They focused on fault tolerant set only, fault tolerant universal set gates on two logical qubits. They did not go with the single qubit, because single sources means we have to focus the conflict only. So other than the conflict, everything will be safe, everything will be better once we go for the single source. But they go for the two logical qubits, and then fault tolerant universal set of gates on two logical qubits are trapped ion on quantum computer. So quantum computer means they use the qubit means they used controlled NOT gate, C NOT gate. With the help of C NOT gate, and then they demonstrated fault-tolerant universal set of gates on logical qubits. And in the year 2023, researchers in Google, as I told in the beginning, so they initially they did not reveal in what situation or in what experimental case or what case study. They initially the previous result will be 3.08% error rate, and then they reduced into 2.914 error. But the basic concept behind this is not yet revealed. But anyhow, they reduced the noise level from 3 to 2.9. So this itself a great achievement. They use 5 qubit array. So 5 qubit array means initially they started a 9 qubit array, and then 7 qubit array, and then 5 qubit array. So after that, nobody enters in the 7 qubit array. So once they go for the combined coding techniques, so like a quantum, classical, and Hamming mode, they themselves need 5 physical qubits. So now Google proved that with the help of 5 qubit array, they initially the noise is 3.028%. They reduce it to 2.914%. So this itself a great success. And then the next experiment in this year is IBM. IBM announced that they reduced, that is the error rate is 800 times better than the physical error rate. So once they use the classical computer, means some error rate is there. So once they same data, same input, instead of classical computers, instead of bits, normal bit, they used qubits. So there they get 800 times better results when they go for the qubit. So this was reached by Microsoft. Microsoft claimed that they in the quantum error correction code was 800 times better than the classical computing. So and then there they are using 32 qubits on quantum strapped ion hardware. So they are revealing the hardware, but they are not revealing the proper case study, where they reached this 800 times better, in which case, in which scenario, or in which situation, or what are the concept behind that, what are the data integrity they followed. But they announced that they reached 800 times better than the physical error rate when they use quantum computing. And then again coming to the parity check. So parity check means in NLP, natural language, quantum natural language processing, sentences is converted into the circuits. So here also when they go for the parity checks, and then again they are involving some kind of circuits. In that circuits they reduces the coherent noises. So detect the noise, and then noise or error, whatever it may be, we can call it as, and then reduce the noise, detect the noise, and then based on the parity measurements, they reduces the noise level. So this is the another achievement based on the parity check. And then how in normal error correction, in the normal error correction we can have when we use for the normal classical computing, we can have that errors like automatic repeat request, and then stop and wait ARQ, go back and ARQ, selective repeat ARQ we can use. But when we go for the quantum error correction, we have two different types of errors. One is bit flip errors, and another one is phase flip errors. So what is a bit flip errors means? And this error is called as X, and the phase flip error is called as Z errors. And then here the values are 0 to 1 or vice versa, 1 to 0 or 0 to 1. But in the classical computing, we have ARQ techniques, that is automatic repeat request technique. Again, that ARQ is classified into 3: stop and wait, go back, and then selective repeat ARQ. But here we have two main types of errors. One is bit flip. So this is called X errors. So either 0 to 1 or 1 to 0, vice versa. And phase flip errors is 1 to -1. There is no zero concept here. From 1 it will go to -1, and -1 to 2. So but bit flip errors is 0 to 1, and the phase flip error is 1 to -1. So this is the basic difference between quantum error techniques and classical error correction, quantum error correction and classical error correction. And then measurement. So when you go for the measurement, information, so informations in the when we go for the quantum error correction, we cannot disturb the information. So we have our information as it is. We never lost our information, but we have to we will reduce the error only. So obviously our informations are with us. With the help of Pauli operator, already we saw the unitary operators. With the help of Pauli operators, we can keep the information, we can keep the data as it is. So we will not lose any kind of data. So what is Pauli operators means? Pauli matrices are all nothing but 2 by 2 complex matrices, and this is traceless matrices and involutory matrices and unitary matrices. So previously we focused only unitary matrix, but when we go for the Pauli operator, unitary comes inbuilt in it. Unitary is an inbuilt operator in the Pauli operator, and it is a complex matrix. And in the complex matrix, if it is a 2 by 2 matrix means it is a traceless matrix, and then it is a involutory matrix. So once you go for the quantum error correction, so you have to focus the Pauli operator. Pauli operator means unitary operator inbuilt. You have unitary operator inbuilt, it has a traceless, and inbuilt it has a involutory. So we have to focus all those things for the quantum error correction. And then what kind of problem domain, how can we identify the problem domain? Once we identify the problem domains means we have to compute our problems. So either you have to go with the optimization, or you have to go with the simulation, or machine learning, or cryptography. So we have to identify. Optimization means you need to focus optimization alone. Simulation means we need to focus simulation alone. And then or you will go with the machine learning, or you will go with the cryptography. So you have to identify the problem domain. And then problem case means what kind of mathematical formulation you are going to follow, what kind of computational complexity you need to overcome. So those things should be identified by us. So this is the problem case. You have to identify the domain. Once we identify the computational domain, then we need to focus. I'm going to focus only optimization, or I'm going to do the cryptography concept. Like that we need to fix ourselves. Then problem class, how to identify the problem class means you have to use the same mathematical formulation or same computational complexity of classes. Then after that you need to identify a model. Then you need to find out any kind of algorithm. So identify the model. That model should simplify the existing one. So your model should simplify the existing model, and then don't go with the complicated algorithms. And then as I told, no, you have we have to decode. If we want to be expert in this quantum computing means we should decode any paper. Let us assume, so I'm going to consider this paper, scalable distributed gate model quantum computers. So here also they are using NISQ, noisy intermediate scale quantum. So here I took this paper. I'm going to identify the system model. So identify system model means I'm going to get the quantum nodes. So here this is my data. So as I said, data integrity means schema. So I told the triplet, no, schema. In that triplet we have a global schema, and then heterogeneous source, and then mapping between the heterogeneous scheme and global scheme. So that is a triplet. But here quantum node, and then entanglement conditions, and then mapping between this quantum node and the entanglement conditions. So we have to identify the quantum node, and then this is the entanglement. So and then we have to find out the mapping between these two. Mapping between these two is nothing but d of, that is distance between any two variables, that is in the two-dimensional distances, 2 power L minus 1. And then this can be decoded like we can distributed unitary concept you need to apply. So you are not with the centralized one, and then initially distributed unitary. So the distributed unitary values means your pair will be zj zk and then gamma of jk. Then you can split it, that is decay it like this. Then you go with the exponential. So this is nothing but e power minus I theta. E power minus I theta This is, let us assume this is a theta. So e power minus I theta means I can write it as e power minus I theta means cos theta minus I sin theta. I'm going to consider this is my theta. So when this is my theta means e power, this is my theta means cos theta minus I times of this theta, again zj minus zk. Similarly, e power minus I theta means cos gamma k minus I sin theta, again gamma k zj minus zk. Then multiply these values, apply some basic algorithms, then you will get the solution. So this is the way you need to decode it. So how this is the way you need to decode means this is the paper. So in this paper, we are going to consider this is mathematically you have to consider the qubit, and then j, k, z are your qubit. Then this qubit is applied into the values z, k, gamma k. Then you have to decay it. Decay it in the sense divide it. Divide it means adjoint and then unitary operator you need to focus. Again here they are using poly operator. So it's very simple. Mathematically we approach the quantum computing means only two operators you are following, only one not C not gate you are following. So you are well versed in poly operator and unitary operator, C not gate. Then exponential, you should know how to decay it exponentially. Exponentially decay it means you have to divide it in one component is divided into two component or three component or more than two components. Once you divide it into two components, then you need to go with the exponential decay. So exponential decay means we know that e power I theta equal to cos theta minus I sin theta. Then so you will get this step, you will get this step. Then after that do some kind of, go with some kind of trigonometric properties, simplify, then you will get this. Simplify, then you will get this. So the entire concepts are based on poly operator, unitary operator, and some kind of C naught property. That's it. So these are all the major role here. So if we are well versed in these concepts like optimization, scalability, data integrity, redundancy, then we can be a somewhat capable of doing something related to quantum. So quantum computing obviously will be a game changer. And then it, quantum computing invites us to dream big one more time. Already we dream big, and then we identified artificial intelligence, machine learning, deep learning, so many things. Again, quantum computing gives an opportunity to dream big one more time. So it's a very good chance. So I think in our lifetime, so almost we are in 30 to 40 or 40 to 50, in our life period we will not have this kind of dream big one more time in our lifetime. So this is the right path to develop ourselves, to enrich our knowledge in quantum computing, so we can do wonders. Nowadays so many premier institutions and then premier companies are offering good salary for quantum engineers or quantum physics. These are all our references. And then thank you. Any questions or any doubts, then we will go, because my
Yeah,
time is.
participants, if you have any questions, please. The participants, if you have any questions.
And I'm somewhat mathematically doing good in this quantum computing. So if you have any help related to mathematics, like a like a optimization or a data integrability or scalability, then I'm ready to help you. So you can get my mail ID from Srinivasan sir. I'm always ready to help. Mathematically, I can do something for your research in quantum related.
Thank you so much, ma'am, for presenting such a valuable and compelling session. It's really very informative. Thank you so much, ma'am.
Thank you, sir. Thank you, sir. Thank you, sir.
So dear participant, the session feedback is available in the chat box. So kindly take a moment to fill out the feedback form. So the link will be shared shortly. So once it is done, so we will start the next session. So dear participants, kind attention please. So we are getting lot of bulk messages regarding this attendance issue. So already we are updated the things. So as soon as possible, we updated the daily attendance in tomorrow. So we kindly request you to remain patient during this process. Thank you.
Hello.
Hello.
Sir, good evening, sir.
Good evening, sir.
Sir, I AIT's department with the Tamil celebration, sir.
No, sir.
Sir, actually,
So dear participant, the session feedback link is available in the chat box. So kindly take a moment to fill out the feedback form.
Vinod, you can start.
So dear participants, so we are move on to the next session. So it's my great pleasure to welcome Dr. M. Nalini, Associate Professor and IEEE Senior Member at SA Engineering College, Chennai. So Dr. Nalini is an esteemed academician with over 13 years of teaching experience, and she has made outstanding contribution to the field of research. Dr. Nalini has authored and published book chapters with renowned international publishers, including IGI Global, Taylor and Francis, and Springer. Her research work with 61 published articles in diverse areas such as data mining, wireless sensor networks, and cloud computing. So it advancing knowledge in this critical field. In addition to her scholarly published, Dr. Nalini has contributed to academia as a reviewer for several reputed journals and has been active participant in international conference. Her dedication to research has been recognized with numerous prestigious awards, including Best Research Award in 2019 and Best Women Faculty Award in 2020. Today, we are privileged to have Dr. Nalini as a resource person for this session on error correction in quantum computing techniques and challenges. Her vast knowledge and expertise in the field will surely provide us with valuable insights. So, on behalf of everyone here, I welcome you, ma'am.
Thank you, sir.
Welcome, ma'am.
My screen is visible.
No, ma'am. So now you can share your screen, ma'am. Yes, ma'am. Now it is visible.
Thank you, sir.
Okay, ma'am.
Good evening, everyone. Today I am excited to share and explore the basics of quantum computing, the necessary for quantum error correction, the challenges involved in this, and the techniques used to overcome this. By the end, definitely you will have a clear understanding of this pivotal topic in quantum computing. First of all, we are going to see about what is quantum computing. With a little introduction, we will go for our main topic. Quantum computing, leveraging the principles of quantum machines to perform computations far beyond the capabilities of classical computers. Unlike classical bits, which one and only exist as zeros or ones, the qubits can exist in a state of superposition, representing both zeros and ones simultaneously. This combined with enlightenment and interference allows quantum computers to solve complex problems much faster than their classical counterparts. So, why do we need quantum computing? The need for quantum computing stems from its ability to tackle problems that are infeasible for classical computers. For example, including breaking cryptographic codes with short's algorithm and optimizing complex systems through the quantum analoguing and accelerating machine learning process. The quantum computing allows us to simulate quantum systems in fields like chemistry and material sciences. For opening the doors to new discoveries, this is very important. This application span across industries from healthcare, finance, marketing, etc. Why do we need quantum error correction? Because quantum computing exploits the quantum mechanisms, principles like superposition and entanglement, allows the qubits to represent both 0 and 1 simultaneously. Quantum systems are highly error due to decoherence and quantum noise. The quantum error correction is essential for producing quantum informations from these errors. Then only we can able to recover the errors are possible. The qubits are initialized as a superposition, that is we called as psi is equal to alpha of 0 plus beta of 1. This is the common equation. We'll explain these in the next. So now we need to see about why quantum versus classical error correction. In classical error correction, uses the redundancy like a repetition of codes, but the quantum error correction is more complex because you cannot simply copy the qubits due to non-cloning theorem, so that we can't able to copy. Next, the qubit can suffer from both bit flips and phase flip. So what is bit flip, phase flip? We'll explain it in the next session with the presentation. Measuring a quantum state can describe it, so non-descriptive error reduction also required here. So this is mainly focus on 0 tends to 0 and 1 tends to ones and zeros with the example. So now the main part we are coming into this, that is quantum errors. So before quantum errors, we'll see the introduction about quantum error correction. In the quantum error correction, the common quantum error is a superoperator equation of rho tends to sum of ak rho ak cap. So this is the common equation for the quantum error. In this equation describes how the quantum state, that rho, it is a density matrix, represent the state of the qubit position. How these involves with the errors. That errors is called as a sum of ak. It is also one of the operations of the possible errors. Another one, the row of ak cap, that is also another one kind of possible error. So that is we called as Hermitian conjugate. That a cap we called as ak of cap we called as Hermitian conjugate. This Hermitian conjugate is a complex conjugate transpose. This ak of that symbol T symbol, it is called as a complex conjugate transpose. The sum over these ak row of ak transpose allows for the possibility of multiple types of errors. With the mixed manner, we can able to solve it. That is possible with this here. So here they are mentioning the single qubit errors. The first error is bit flip error. That is we called as X error. Another one name of bit flip error is X error. So here the equation of X divide 0 wrangle is equal to divide 1 wrangle, or the opposite of this, X divide 1 wrangle is equal to divide 0 wrangle. This is similar to classical bit flip. Here we can able to tuning A into 1 or 1 into 0, vice versa. We can able to share it both the sides, that is possible. Another error is the phase flip error, that is we called as Z error. Here we have Z divide 0 wrangle is equal to divide 0. Here 0 means it is equal to 0, but in bit flip, if it is 0 means it is equal to 1. Another one, vice versa, if it is 1, it will be 0. Likewise, it is opposite, 0 to 1, 1 to 0, that is bit flip. In phase flip, the errors we called as Z divide 0 wrangle is equal to divide 0. If it is 0 means 0. Okay. Another possibility is Z divide 1 wrangle is equal to minus divide 1 wrangle. So this types of error affects the relative phase between the basic states but leaving the qubit measured values because it is unchanged. Next type is complete dephrasing. So here the complete dephrasing we called as decoherence. Another one name is decoherence. Here the general term is rho tends to open bracket rho plus z rho z transpose divided by 2. So here they are meaning as z means what? Z errors, that is phase flip errors. So the quantum state to lose the coherence effectively because mixing the state with its phase flipped version, so that this is going to be happen. Based on this equation, we know that complete loss of coherence between the components of the quantum state is going to be happen here. The another one type of error is what? Rotation error. The rotation error we called as R theta divide 0 wrangle is equal to divide 0 wrangle. Another one possibility is R theta of divide 1 wrangle is equal to E I theta divide 1. So this is the equation for rotation. Here how the theta is going to be shifted from one phase to another phase because of error that we can able to see. This error indicates the phase shift of theta to the 1 wrangle divide 1 wrangle divide 1. This is the state. For the rotation, errors are continuous. The errors that can gradually accumulate and cause the deviations from the intended quantum states. So that is we called here as a rotation operation that introduce a phase shift by a angle theta to the theta I theta. So for this we have an example of a bit flip error might turn the state divide 0 wrangle or 0 wrangle. This will be can be correcting using error correction codes that detect such errors by measuring the parity. So here just we seen that what is quantum errors and its error types. What is the equation for that? Now we are going to see about the classical error correction. How to do the classical errors correction. Next we are going to do the next type of error corrections. Here in this the classical error correction, the classical computing to correcting the errors and realizing the redundancy and these techniques such as repetition codes. This repetition codes parity bits and extra information to detect and correct the errors here going to be happen. For this instance, if we transmit the message 1010 multiple times, any discrepancy can be resolved by comparing these repeated copies and selecting the majority. So while effective for classical systems, these methods cannot be directly applied to quantum systems due to their unique properties. So the error detection and correction is the majority rule to be playing here. The classical repetition code, the repetition code is a simple, effective method. We encode bits by repeating them as 3 times, like 0 to 0, 0, 0 and 1 to 1, 1, 1. In 1 bit flip, due to the noise, we can correct it by taking the majority vote. Okay. Here, based on the correction, how it is going to be happen now? 0, 1, 0 is belongs to 0 means the answer would be corrected as 0, 0, 0 because here the 1 bit error is turned as 0 to 1. So that 0, 1, 0 is coming. So after the error correction, we will get the answer as 0, 0, 0. After classical repetition code, we can get it. Now, no cloning theorem. How we will apply this no cloning theorem here with the example. The no cloning theorem states that it's impossible to create an identical copy of an unknown quantum state. So that they are telling us that is no cloning. Cloning is not possible here. The same duplicate repetition that is not to be here. The proof is based on linearity. If such cloning mechanism exists here, with this equation divide 0 wrangle tends to divide 0 wrangle divide 0 wrangle, or 1 wrangle tends to divide 1 wrangle divide 1 wrangle. If it is 0 means 0, 1 means 1. So this cloning mechanism exists. It would produce contradictions when applied to superposed states. Here linearity is given as alpha divide 0 wrangle plus beta divide 1 wrangle. So addition of these two alpha and beta, we are getting alpha divide 0 wrangle divide 0 wrangle plus beta divide 1 wrangle and divide 1 wrangle. The combination of alpha is 0 means we are getting the answer also alpha divide 0 wrangle. If beta divide 1 means we are getting the answer is beta divide 1 wrangle. The mixed combination of zeros and ones, it is not possible here because the cloned state would violate the principles of quantum mechanism, as the outcome would not be simple produced of two identical qubits. So that is not possible here to do the cloning. Next, the barriers of quantum error correction. The quantum error correction faces unique challenges. The no cloning theorem is the first challenge. Another one is the superposition. Another one is the entanglement. Next, measurement issues. In no cloning theorem prevents direct copying of quantum states. In superposition, it means errors can affect multiple states simultaneously, while entangle the cases errors in one qubit to impact others. Additionally, measuring the quantum state collapse them to complicating the detection and correction of errors due to measurement issues. The measurement destroy and superpositions. If we try to apply the classical repetition codes directed to quantum states, we encounter a major issue, that is measurement collapse the quantum superposition. Example, the state alpha of divide 0 wrangle plus beta of divide 1 wrangle tends to alpha divide 0 0 0 wrangle plus beta divide 1 1 1 would collapse to either the bit flip error of x on the second qubit, so that we are getting the answer as alpha divide 0 1 0 wrangle plus beta divide 1 0 1. Here we are destroying the quantum information. To address this, we need techniques that measuring the errors without measuring the qubit value, so that the second bit is different from first and third bit, so that it will looks like different. Without finding its actual value, the qubit value is differing. Measure the error, not the data. Here, the encoded state is showing here with the error syndrome. How these are affected. So, unclear qubits or extra qubits used to prove the systems for errors here. Here, the error syndromes are the result of the indirect measurements that indicate when the type of error has occurred without revealing the actual state of the qubits. This process is ensured the superposition is mentioned while correcting for errors like bit flips or phase flip, that is Z errors. This method allows us to perform the quantum error correction while preserving the quantum data, which is essential for the stability and scalability of quantum computing systems. So from this we can learn about error without learning about the data. So the superpositions are preserved based on this. So to preserve the superpositions, we need to measure only the errors without learning the actual value of the qubit. For that, we need to introduce the qubits that help to detect the error syndrome. For example, a circuit like extra errors informations while keeping the data interactive with inside, so that we can be able to preserve. Next, redundancy and repetition. The first error is going to be occur based on the redundancy. Redundancy is nothing over here. The repetition is going to be occur. Quantum error correction realize the redundancy and not repetition. Then only the quantum state is spreaded across multiple qubits. In this way, that errors can be detected and corrected without involving the non-cloning theorem. This process preserves the superposition while encoding the information redundantly. So for that, here they are mentioning alpha divide 0 wrangle plus beta divide 1 wrangle it is belongs to alpha divide 0, 0, 0 triangle plus beta divide 1, 1, 1 triangle. So this is not equal to alpha divide 0 plus beta divide 1 triangle and the tensor product of 3. So correcting this phase errors, we need to do the quantum systems can suffer from phase errors where the phases of the qubit flips between h of alpha divide 0 angle plus beta divide 1 angle is equal to alpha divide plus beta divide minus angle. With x errors, x divide plus angle is equal to 1 plus triangle or x divide minus triangle is equal to minus divide minus triangle. This acts like as a phase flip. So here we are mentioning as x, anyway it is a phase flip. Next, bit flip. So in bit flip here we are using the wording as z divide plus triangle is equal to divide minus triangle or z divide minus triangle is equal to divide plus triangle. The repetition codes in a Hadamard basis can correct the phase errors just like bit flip errors. In bit flip errors, the alpha divide plus triangle plus beta divide minus triangle, it belongs to alpha of plus triangle. After that, we are adding beta divide by minus. So we can detect and correct this by using quantum error correction circuit designed for phase errors. Next, 9 qubit error, 9 qubit code. So we can say like this 9 qubit code as SHARP code. This SHARP code encodes 1 logical qubits into 9 physical qubits. To protect against this by both bit flip and phase flip errors. So from this we can able to protect it. Make use of alpha divide 0 triangle plus beta divide 1 triangle. This is belongs to alpha open bracket divide 0, 0, 0 plus 1, 1, 1 triangle tensor product of 3 plus beta product of divide 0, 0, 0 triangle minus divide 1, 1, 1 tensor product of 3. So alpha tensor product addition with beta tensor product. So from this first 3 qubits correct bit flip errors and the next set of 3 qubits we can able to correct with the phase errors. If a bit flip error occurs in one of the qubits and the remaining 2 can be used to identify and correct the errors means. Similarly, if the phase error occur, then also we need to taken up the qubits into a block. After that, we need to correct it. This code can even correct the combined bit flip and phase flip errors. The correcting continuous rotation. Quantum systems are also continuous errors like small rotations. For this, rotations can be described in a rotation operator. So here the continuous rotation error occurs only when the qubit is slightly rotated. This will be described by the operator of r theta divide 0 angle is equal to divide 0 angle, and r theta divide 1 angle is equal to ei theta divide 1 angle. So this error correction scheme can be still correct such kinds of errors, and we can able to collapsing the state onto the basics. After that, we can allow easily to correct this as possible. From the cos of theta divided by 2i minus I sin theta divided by 2z. So this quantum error correction can measure the error syndrome and determine if the correction is needed by collapsing the state based on the probability of the error. So here r theta k of psi is equal to cos theta divided by 2 divide psi minus I sin theta divided by 2 z of k divided by psi. So here r theta k and the r theta both, it is act like as a qubit of kth qubit. Here the correcting continuous rotation also having the same kind of errors, bit flip and the phase flip, to do the correction based on the rotation. So here we are using the rotation as r theta of k divide psi is equal to cos theta divided by 2 divide psi minus I sin theta divided by 2 z of k divided by psi. So measure these errors. The syndromes collapse the state so that error has occurred. After we are doing the correction step, we need to rectify the errors to get sin square theta divided by 2 is equal to z of k divide psi. Here the z of k is the corrected format compared to the errored format. In the errored format, we have only the psi value with this. So now we need to correct all the single qubit errors. So one of the powerful results in the quantum error correction is that if we can correct these three basic errors, that is, for first one is the bit flip, another one is the phase flip, and the combination of both bit flip and phase flip, that is why. So here we called as a bit flip as X errors, phase flip errors as Z errors, and the combination of these two kinds of errors we called as an Y errors. So we can correct all the single qubit errors. Then this error span all possible single qubit errors, and any quantum errors can be decomposed into these basic types. So here a quantum error correction code that can correct the bit flip of X and the phase flip of Z, and Y errors can correct any single qubit errors, because any 2x2 error matrix can be written as a linear combination of the 2 into 2 matrix. So here the general term we are written as alpha of I plus beta of X plus gamma of Y plus sigma of Z. So here the qubit undergoes an arbitrary error, that is repetition by A's, if the code corrects X, Y and Z type of errors. It can be correct any combination of these errors also possible. After correcting the possibility of T qubit X, Y, Z, we can able to correct it. All t qubit errors is possible. Next, the Pali group. Quantum errors are often described using the Pali group. Here, we consist of the identity of I and bit flip error we called as X, and bit and phase flip error we called as Y, and Z as a phase flip error. These operations we need to consider. After that, this Pali group forms the foundation for describing the errors in the quantum system and help us to understand how to detect and correct these errors. So here we have a combination of bit flip and phase flip as Y errors and phase flip as Z errors, and the identity type as I. Here Pn consists of an tensor product of up to the operator I, X, Y or Z errors. We will have the overall phase is plus or minus 1 or plus or minus I. So any pair of M, N as we will getting as the anti-commands of Mn is equal to minus Nm. Otherwise, vice versa, Mn is equal to Nm. Small errors on every qubit, how we will rectify it. Here, the idea that is quantum computing to reduce the noise. Due to this noise and imperfections in the system, each qubit can be accumulate small errors over the time. So, these errors are not necessarily large, but they can affect the overall state of the quantum system. So here the main concept, every small errors can propagate and impact the computations, which is why error correction is essential. Because of we rectify the errors, after that only we can able to get the correct result. So the error correction is very much essential here. In the quantum computing, that is very important. The quantum error correction codes, that is QECC, quantum error correction codes. What is the aim of this method? To detect and correct these small errors before they accumulate the point where they disturb the computations in entire thing. So here we have types of errors, that is for X errors, Z error and Y error. We know what are the types of these errors, the same common type of errors in the quantum computing, but these are all the small errors in a single phase errors. So these errors occur simultaneously. We need to be multiple qubits concentrate to reduce these errors is important. So in the quantum error correction codes, the short form of U epsilon is equal to I plus epsilon E. So here U epsilon, the tensor product of N divide psi rangle is equal to divide psi rangle plus epsilon open E of 1 to E of n divide psi rangle plus order of epsilon square. So in the quantum error correction code is possible with short codes and Sten codes and surface codes. So here the shard codes encode the 1 qubit into 9 qubits to detect the correct errors. The STEN code is used to 7 qubits to correct the single errors. In the surface code, this is a topological approach. It is used 2D qubit arrays. So, based on these quantities, the quantum error correction codes address various error types. In shard code, encode 1 qubit into 9, allowing these kind of deductions and corrections of both bit flip and phase flip errors we can able to correct it in the shard code. So here 1 qubit into 9 qubit we need to be corrected. In the STEN code we can use several qubits like a 7 qubits or 8 qubit, like several qubits we need to use to correct a single error. That is also the type of bit error or phase error or Y error. For the single bit correction, we need to use 7 qubits. So in the surface code, we have a topology approach. So we are using two-dimensional array of qubits for scaling the error correction. So the quantum error correction code conditions are: explain the specific condition is under which quantum error correcting code can effectively, efficiently is working. Here for the quantum code to correct the errors, it must satisfy certain conditions only. These conditions are typically captured by the Kernel-Laflamme condition, which state these psi I from basis code words and EA, EB is belongs to E. Here, matrix C of AB depend on I and jth column. So here C of AB is equal to del of AB. Then we can make a measurement to determine the errors. C of AB is less than maximum code. It is degenerated. So here the psi of I divide E of A transpose E of B and divide psi of J is equal to C of AB del of Ij. So with the code speed without mixing different code words. So here C of E is a constant that depending on the error E, but not on the code words of I's and J's. So here ensure the errors. We can suppose
Excuse me,
if
ma'am.
the-
Your PPT is not visible, ma'am.
not visible.
Can you share your PPT once, ma'am?
I'm sharing now. You can able to see it. It's
Ma'am,
visible.
your screen is not visible, ma'am.
Not visible. It is in the share mode only. What?
Make it once again, ma'am. So
Oh, yes, yes, sir. 1 second, sir. Again, I'll do it. Unable to share, sir. 1 minute, sir. Now again, I shared, sir. It is visible.
no, ma'am, no.
No. What happened? I don't know. It is in the shared mode only now.
Can you share your PPT to me, ma'am, or else Srinivasan sir? So we will share here, ma'am. Through WhatsApp, you can share it. So we will share it here.
Okay, okay. 1 minute. I will
Okay.
share. I shared, sir.
Dear participant, wait for a few minutes.
Yes, ma'am. Your screen is visible.
Now visible, sir.
Yes, yes.
Now it is visible, ma'am.
Okay, sir. Now we are going to see about the erasure errors. How to erase these kind of errors that we are going to see now. In the erasure, it will be occur based on the position of the error. We know that it is certainly occur based on the certain positions. So we can make it as very easier to correct these kind of general errors. In the quantum, erasure channel is an important model for handling these kind of errors. So make use of that models, we can able to rectify these errors. Here also the types of errors is bit error and phase error and the identical error and the combination of bit and phase error. That is only comes under this erasure errors also. So for this, we can easily rectify, we can able to follow this error handling model, means we can able to rectify it. Here also the psi of I is divide E of A transpose of E of B and divide and psi of J is equal to C of AB and L of Ij. The same whatever we see in the last type of error. The same thing will be happen here. And we can able to correct it in this kind of general errors with the corrected 2T erasure errors. Because we need to follow the model to correct this errors is the easiest way. So for that we need to know the model how to implement it. Next, stabilizer codes. So in the stabilizer codes are a key method of the quantum error correction. So in this quantum error correction, the stabilizer group is the set of Valley operations and the stabilizers which is used to quantum the code word. And it will be meaningly all the stabilizer operations return the code to the state. When we are going to apply and rectify the encoding errors, in that time these errors are going to be done. But these errors is not to be appear as long as it is very short duration and it is eighth and state some of these operations. So simply we will take as the 3-qubit flip code error and the stabilizer group for this kind of code errors to optimize the code. Like here we are using Z tensor product with Z tensor product of IE. So for this kind of pair of product, we'll find out the qubits errors and we can easily rectify those errors are possible. So here in the error syndromes, we need to find the error syndromes. For this, we are using the tool to identify the location of the error. So based on the location of the error, 3-qubit rotation codes are used to measuring the stabilizer operations, and we can able to detect the errors and type of errors based on the help of this tool to rectify the errors. So here basically you will getting bit flip error or phase flip errors only going to occur. So we need to find the location where it is going to be occur. After that, each valid code words, that is here we are mentioned as 0, 0, 0 and 1, 1, 1. So any 0 or 1s we need to take up as a valid code word to apply here with A plus 1 gain vector of Z tensor product or Z tensor product of I. So here we are speaking about identification error and the phase error and the state with the error of first and second bits. So we need to take up and we need to rectify the 8 and value error field. So here in this equation, we can sort out the bit flip error or the phase error based on the location we identified. After that, we are writing this equation as Z tensor product of ZZ. Otherwise, this will be even equal to X tensor product of X. That error is possible. Otherwise, X error also possible here. So, both vice versa, it will be happening. So, that is, we say that the measuring Z tensor product of Z will detect with the bit flip errors. Otherwise, the X tensor product of X we deduct with the phase error. So these errors will find the syndrome and we can able to locate the errors and sort out this method. Next, the stabilizer for 9-qubit code. So here using the 9-qubit short code and the stabilizer operations to correct both flip errors and phase errors. So here bit flip error, phase error only going to be occur. Here the full set of stabilizer that will cover all the qubits in the code. What are the qubits? Like here you can able to see that Z and X, right? So the bit flip errors and the phase flip errors. All the errors we are going to cover up with stabilizer. Here we are using M1, M2, M3, M4, M5, M6, M7, M8. So 9-qubit code. So here we are using all the stabilizer to group all the bit flip and phase flip errors. So here we after the stabilizer, it will convert all the qubits into code. After the code generation, the stabilizer operation to detect any other errors that occurs on the individual qubit by measuring the 8 and values of these operators. So here the short code method, it might be used to stabilize like Z tensor product of Z tensor product of I, tensor product of I, and the tensor product of IZ. This is the term which will be used to rectify the stabilizer errors, to rectify the type of error present in the stabilizer, that is bit flip or phase flip. So after checking the parity between the first and last qubits, the bit flip error or either a qubit would case the stabilizer to yield a 8 and value of -1 signing error. So here the stabilizer consists of value operations of M with the property of M divide psi wrangle is equal to divide psi wrangle for all encoded states of psi. So here the properties of stabilizer. Stabilizers from an abelian group. The meaning of all the stabilizer operations command within another group, that is the main property here. This property is crucial because we can ensure that errors can be detected without interfacing from these stabilizers. For a code with triple N and physical qubits and triple K logical qubits, and the stabilizer group has n to kn bits, we can able to generate. So here in this equation, m divides I is equal to divides I, and n divides I is equal to divides I. So here that is m or n divides I is equal to divides I. So here the m divides I is equal to divides I and n divides I is equal to divides I. So these two are, we are going to subtract with mn or nm with the psi value. We are getting the value as equal to 0. In polymetrics, in abelian groups S of poly operations also, we can get the code space T of S. T of S is equal to divides I and M divides I is equal to divides I for all M belongs to S. If M is belongs to F, then it is possible. Then T of S also we can able to encode it with the K logical qubits from n physical qubits to n qubits. Here, yes, we will taken as n of k generators. The stabilizer elements to detect the errors. So based on the stabilizer, how we will detect the errors. Here also the error types must be common in the 3 types of errors. Here in the case of occurring anti-commands with the stabilizer element of triple M, and it will the ATAL value of triple M from +1 to -1. By measuring the stabilizer value, we can detect the qubit has been affected by this error. So here M belongs to S and the poly errors of E anti-commands with M. So here in this equation, M of E divides I random equal to minus EM of divides I wrangle is equal to minus E divides I. So here E divides I is an ATAL value. It will be belongs to -1 from M. Likewise, if it is M is belongs to S, then M of E divides I wrangle is equal to EM of divides I wrangle is equal to E divides I. Not a minus value, it is a E divides I. Why? Because of for all M is belongs to S, then it is not comes under the minus value, ATAL value. Here plus ATAL value we will taken as E divides I as an plus ATAL value because of M in the stabilizer. So that the ATAL value of the operator of M from the stabilizer to detect the errors which anti-commit with the M. So distance of the stabilizer code we will taken up. The distance of the stabilizer code refers to minimum weight of the operator that commands with all stabilizer but is not itself the part of the stabilizer group. Why? Because of the code can be detected and correct the errors as long as the number of errors is fewer than the half of the distance. So from this, the stabilizer group S and the distance triple T we will taken as the small non-trivial value operations of triple N, such as we will taken as N of S is equal to N belongs to P of N and Mn is equal to Nm. If it is then vice versa for all MS belongs to S. So here in this, to detect any errors not in N of S or divided as S, which commit the stabilizer which are not detected. So next the error syndromes and stabilizers. It will be used to correct the errors with the enough information must be collected to determine the exact nature of the error. So each error syndromes are correspond to a specific combinations of plus or minus latent value of the stabilizer operation. Based on this, we are going to correct the errors. If it is MS belongs to S, we can easily correct the errors. The stabilizer code corrects the errors in the way of stabilizer code can correct triple T of errors. If it is the distance as triple T, it will be satisfied the equation as D is equal to 2T plus 1D is equal to 2T plus 1D is equal to 2T plus 1. So here in this code, we are going to distinguish between different errors by the syndromes, and any two errors with the same syndrome will be treated as equivalent for the correction purpose. So here they are mentioned as D is equal to 2T plus 1D, or else it will be as 2T plus 1T. Here in the case E and F has same error syndrome, then E and F commence with same element of S. So E transpose F is belongs to N of S, and E transpose F is belongs to S, then it will be E transpose F divide side wrangle is equal to divide wrangle. So the distance is mean here as D is equal to 2T plus 1. The stabilizer code, the distance is triple T determine the number of correctable errors. That is T is equal to D minus 12T is equal to 2D minus 1. In the code, the distance 3 will taken as the correction of one error. So here we can choose the abelian subgroup of the Pali group as a stabilizer first. Next, we need to choose it as the code words or the plus of 1, 8 and states of the stabilizer operation. Finally, we need to take in the number of encoded qubit as the k values. We need to determine the number of stabilizer generated as R. It will be taken as k is equal to n minus rk, or else it will be taken as n minus rk. Here S as R generations of n qubits means we will taken as k is equal to n minus r. But here in this case the stabilizer generates triple R, then we will taken as a k is equal to n minus rk. So here in the 7 qubit code we will using then n is equal to 7n, and we will taken as an r value is equal to 6r and the k value as 1k. So we will taken as a logical qubit as encoded with the 7 physical qubits. So here E transpose of F is not is equal to N of S divided by S. Because of all the pairs of E to F, we will taken as this kind of errors. So next the application of qubit code. So here the 5 qubit code is a well-known example of the stabilizer code that encoding the logical qubit into 5 physical qubits. It has the distance of 3. The meaning it can be correct any single qubit errors. So here we are taken as an n is equal to 5 physical qubits minus 4. We can able to generate the S as k is equal to 1. Already last slide I said that k is equal to 1 encoded the qubit because of the distance d of the code is 3. So the stabilizer generates for the 5 qubit code or combinations of Pauli X and Z operations such as X tensor product of Z, tensor product of Z, and tensor product of X and tensor product of I. So from this encoding k logical qubits in a n physical qubit distance of D. From this we can get a 5 qubit code, that is non-degradable codes of QECC. We can able to get it. The smallest QECC means we will taken as whether the smaller code of 5 qubit code and exit while still correcting one general error. So from this we will taken as the answer is number, that is for 4 qubit code, and it will cannot correct both bit flip and phase flip errors as effectively as the 5 qubit code. It will be corrected only 5 qubit code as a smaller code, but it is not taken as the answer to correct it as 4 qubit code because of each pair of qubit as 2 erasure errors will be there. So here the cloning also is going to be happen because of the duplication. This is not acceptable for the quantum error correction, the cloning technique. In the classical linear code also will be defined using parity checker matrix for removing the errors and correcting the code. For this, and the parity these will be held the errors to ensure the code word of V. It will be satisfied HV is equal to 0 HV or 0 HV is equal to 0. Here V is belongs to C. C is the linear thing. So V comma E is always belongs to C. So we can get the answer of V plus W is belongs to C. Here the coming code is the linear code. Single bit. Yes.
Sorry for the interrupt, ma'am. Your voice is not clear, ma'am.
So here n is equal to 2 or minus 1 L. Here this code has the distance of 3 if the error E has weighted as 1. So from this we will getting as an humming code for R is an n is equal to 2 power R minus 1. So K is equal to 2R power minus R minus 1. Here in the linear code also, we will get the values as the classical linear code can be transformed into quantum error correction codes by replacing the 1s into the parity checker matrix with the Pauli triple set operations. finally, we are going to see about the CSS code. So CSS code is the Calderband Short Steeman code. This is the class of quantum computing error correction code. This will be combined two classical linear codes and one for bit flip code, another one is for phase flip code. Based on this parity checker matrix of one classical code is used to detect the bit flip errors. While we are getting the deduction of phase flip error, we'll get the answer as for 743 as a humming code. Here 713 is a CSS code, one classical code that is humming code. It will be correct the bit flip code and another one correct the phase flip code. The code products one logical qubit using 7 physical qubits. The values for one logical qubits, we are using 7 physical qubit. So that the code distance is of 3. So we are getting the answer as 743 as the humming code value. Thank you for all. Are you able to hear? Do you have any doubt, any queries?
Yes,
Let
ma'am.
me
Yes,
know.
ma'am. Dear participants, if you have any
Sorry,
queries,
here's some audio
can feel
issues
to-
from my side also. If anything, definitely let me know.
dear participants, if you have any queries,
Hello.
Hello.
Yeah.
Hello.
Yeah. Tell me, sir.
Can you hear me, ma'am?
Yeah.
This is Prashant, ma'am. I have one
Yes.
question, ma'am. Hello.
Yeah, tell me, sir. I can able to hear.
Yeah. What is the significance of the difference D of the quantum error correcting code, ma'am? Hello.
What, sir? Again?
What is the significance of the distance D of a quantum error correcting code, ma'am?
Oh, the distance D value you're asking. So the distance
Yes,
D
ma'am,
is
yes,
the minimum number of qubits, sir. That
Okay,
is,
ma'am.
we need in any one valid code word means we can
Okay.
able to change it into another value. Because of how means it is the smallest weight of the operation. We are using
Okay.
taken as a smallest weight operation. From this, we can able to change the code word into the stabilizer mechanism. So after applying the stabilizer mechanism, it is corrected as TRS. So D is equal to 2T plus 1. So you can able to get the distance D as D is equal to 2T plus 1. This will be mean to measure the distance as 3. How it is means that our bit flip and phase flip error, otherwise the combination of the combined errors we are going to be addressed here. So from this we are calculating the distance as it is 3 with the value of D is equal to 2T plus 1. Here the T value is 1. So we are getting the final answer as 3 here. Because these things are done it with 5 qubit code. So the distance we are using as 3. So we are taken as the denomination value as 513. If you take it, then you can able to get the correct answer.
Okay, ma'am. Thank you, ma'am. Thank
Any
you so
other
much.
questions?
Thank you.
Hello, madam.
Yeah, tell me, sir.
Ma'am, Rajiv Mulimani, madam, this side. I just
Yeah,
want to
tell me, sir.
understand what does stabilizer code do in quantum error correction, madam? What is its role in quantum error correction? Stabilizer code.
In stabilizer, sir.
Yes, ma'am.
What is the role of stabilizer you're asking us, sir?
Yes, ma'am.
the stabilizer mechanism, the tool we are using, right, sir, that tool we need to take, and then only we can easily rectify that error, bit error or phase error, and the combination of bit error and phase error will be there. So these errors we will apply directly with the quantum error correction method, means it will be tough to rectify it. But in the small field error we seen in that stabilizer mechanism, so here we are applying means we can able to rectify that our bit field and phase field, otherwise the combination of identified field error. Make use of this tool we are applying means in single error phase value we can able to rectify it, sir. That is possible with the stabilizer mechanism. Without using stabilizer mechanism tools, we are applying means that is not possible with the single error clearing mechanism, sir.
Apart from that, ma'am, I understand, ma'am, what you said, but the thing is, the toric codes and other surface codes are there in a practical relevance when it comes to quantum computing. There are practical relevance wherein surface code, toric codes, and special cases stabilizer codes are being best in performing error correction codes, ma'am. How do we? Which tool do we use, ma'am, for that? Which platform? Theoretically we know how to do the function and how to write the equations, we know, but when it comes to the practicality or doing a hands-on, how do we, which tool do we use? Can you help us in understanding the simulation tools or anything wherein we can use them, ma'am?
Simulation tools. For practical implementation, answer.
Yes, ma'am. Yes, ma'am.
In Intel also we have a quantum simulator tool in the freeware will be there. That simulator also you can able to use and simulate our things is possible, sir. That is available. For our purpose, we are using that alone.
These algorithms we can do the error correction. We can do.
Yes, sir. Error correction is done with that Intel quantum simulator. We can able to do it.
Intel.
Another one that blue qubit also will be there, but that is somewhat tough compared to this. In Intel quantum simulator, you can try it, sir. This will be help you, and it will be somewhat easy to install, and you can able to do it, and it will be supporting.
Okay, ma'am. Okay.
But blue qubit, that also few members are using, but that is some issues with that supporting issue.
Okay, understood, ma'am. Understood. Apart from that, ma'am, one small thing, ma'am.
Yes, sir.
Apart from this one, I got the clarity. When it comes to running an application, ma'am, certainly like doing any image processing or doing any object detection, can we do any real-time application to existing tools, ma'am? Like in the previous session, they were speaking about Qiskit, IBM Qiskit. In that, we can run the normal applications also, ma'am.
Yes, sir. You can able to run it, but the data you're telling us an image processing, the data sets you are collected and you are doing, right?
Ma'am.
That is if you using it in correct measurable way and the correct location, you can able to, because of some supporting that formatting and supporting issues we are facing. So that we think that is not possible with the real time data. Whatever will be there, like that we will ensure it. But we need to work hard with the data to specify that particular measurements. If you correct it, definitely it will be working with your real-time data also, sir.
If we don't have any reference, ma'am, I am not trying to compare it with the existing data set. Apart from that, I am trying to do it from the scratch. From the scratch only, I am trying to do it. Then it will be possibly running correctly, ma'am.
Yes, sir. Yes, sir. Definitely it will be running, sir.
Okay, ma'am.
You can try it, sir. Definitely it will be.
Yes, I am in the process of doing that practicality, ma'am. Just going through the coursework.
Oh, sure, sir. Sure.
Thank you, ma'am.
Oh, okay, sir. Definitely we'll try, sir. It will be working, sir.
Yes, ma'am. Yes, ma'am. Thank you.
Thank you so much, ma'am, for presenting such a valuable presentation. Thank you so much, ma'am.
Thank you, sir. Thank you. Thank you, everyone. If you have any other queries or anything, definitely you will be touch with me in mail communications. I'll given my mail communication and my phone number also to sir. If any doubts or anything, definitely let me know anytime. Thank you all. Thank you for this opportunity for everyone.
Thank you.
Thank you.
Thank you.
Thank you, ma'am. So
Thank
the
you so
dear
much.
participant, the feedback link is available in the chat box. So dear participant, the feedback link is available in the chat box. So one more important announcement to the audience. So assessment exam schedule for tomorrow. So the consist of 25 questions. So it is MCQ questions. So exam link will be activated by 6:30 p.m. tomorrow. So it is for 1 hour, 6:30 to 7:30. So the link will be valid for 24 hours. So kindly note it. So assessment exam is scheduled for tomorrow. So it is consist of 25 questions, that is MCQ. So it is valid. So it is 1 hour test. So 6:30 to 7:30. So the link will be valid for 24 hours. So the exam link will be only for enabled for participants, those who are attending more than 5 days. Dear participant, assessment exam schedule for tomorrow will consist of 25 questions, that is MCQ.